Okay, so let's start with the first question. Right, so for question one, so it is simply about doing the Laplace transform. So for part A, so you're asked to do the Laplace transform of this function. So it is t cosine t. So by the definition of Laplace transform, then you can immediately write down this expression. Okay, then my questions to you would be, do we really need to evaluate this integral explicitly? Or is there any other smarter way to do this transform?
It is the minus DDS.
Correct. So you can actually see that we can write the integral here in terms of a derivative. So you should observe after taking the derivative with respect to s, then you have minus t here. Then you should recover the expression above. So you do not really need to do the tedious calculation by doing many times of integration by parts, but instead you can just write it as a derivative, and because you know what is the Laplace transform of cosine t is, then it is simply s over s squared plus 1. And then in order to get a result, then you just do the derivative, then you would get minus 1 plus s squared plus 1 squared. So let me remind you the Laplace transform of a cosine functions is, so we have a cosine omega t, and the Laplace transform is s over s squared plus omega squared. So we have omega to be equal to 1 here. So we have s over s squared plus 1. Okay, then move on to part B. So for this question, the function is e to the power 2t times sine t. So it is just e to t sine t e minus st dt. Then obviously you are not supposed to do the integral explicitly. So what can you do?
Can we do change of variables, because we now can combine the e as e to the power minus s2 times t.
Yes, correct.
Can yeah.
But you don't really need to do the change of variable, because so here you can absorb the 2 into the exponent here. Then because the s here is not a variable of integration. So basically what you have gotten here is just the Laplace transform of sine t of s minus 2. So instead of s, you have s minus 2 here. So let me remind you the Laplace transform of sine is omega over s squared plus omega squared. So here we have, so omega here is 1. So we have 1 over s minus 2 squared plus 1. So there is part B. Okay, so is there any questions about part A and B? If not, then let's move on to question 2. Right, so here you're asked to do the inverse transform. Even you have a Laplace transform of some function ft, then what is ft?
Can we first decompose s plus 4s plus 5 as s plus 5 and s minus 1?
S plus 5, s minus 1. But uh, s plus 5, s plus minus 1.
Yes. Is it correct? Wait.
But you shouldn't have a minus 1 here. Right,
It should
you have
be.
a plus 5. Plus 5
Oh,
times minus
wait.
1
Right.
is minus 5.
Wait. My idea is to decompose the factorize for mole, and then use the node as the product of 1 over dude times 1 over dude prime, because I don't, the dude prime isn't equal to dude. So
you can, but so you are suggesting to factorize it into the form like this, right?
yes.
But if you really do the calculation, A and B, they are actually complex.
Oh,
But,
okay.
but they can be complex, but I will talk about it in the end of the class.
Okay.
But let me remind you. So maybe you may not be aware of the parameter s or the variable s here. Actually, the s here can be a complex number. But I think in the natural notes, you only deal with the real numbers, but it can be complex. So what we can do here is so we can write it something like this for s plus 4 plus 1, right? And we can do the computing square to get s plus 2 square plus 1. Right, then you should
It's
be
actually the
familiar with,
sine or cosine should be.
yes, then so here you have the minus 2 here, right? And then the inverse transform is e to power 2t sine t. And then in question 2, you can see that it looks very familiar with the Laplace transform that you have in question 1. In question 1, it is minus 2 plus 1 is s minus 2. Then here you have s plus 2. Then there should be some relationship.
There should be e minus 2t plus times sine t.
Right. So actually the ft should be e minus 2t sine t. So so um so the fact is when you have some function ft multiplied by EAT, and then you do the Laplace transform. So then you can write that something like this. So what you have here is simply the Laplace transform of the function f itself, but instead the argument is s minus a. So whenever you have observed some functional form that looks familiar with the Laplace transform that you know, but offset by some constants a, then the inverse transform is simply the inverse transform of the function, the 1 over s squared plus 1, which you are familiar with, and multiply with the exponential term here. So it's simply, so what I mean is and a shift in the Laplace transform is corresponds to multiplying an exponential term in the time domain. So it's a Laplace domain, a shift in the Laplace domain. And what you have in the time domain is an extra factor, e to the power at. All right, so to summarize what you have learned in this example, so whenever you have you're asked to do the Laplace transform of some function multiplied by t, or in general it can be t, k. So if you really do the calculation, you should be able to prove that. So if it is k rather than simply 1, then you should show that it is simply minus 1 the power k and d k d s k and fs, because you have here is t k f t e to the power minus st, then it is equivalent to differentiate the integral here with respect to s. So you want t k, then you differentiate. So because by differentiate it once, then you would get a minus t. So you want t to the power k, then it is simply differentiating it by 3 times. Also, you have the minus sign here, so you have the minus 1 to the power k. And then the second thing would be simply the one I have wrote here. So so in the Laplace domain, or the S domain, so a shift in a Laplace domain corresponds to multiplying the time domain function by an exponential factor. Okay, so is there any questions before I move on to discuss how do you interpret the Laplace transform? Okay, no questions? Right, then let me give you a bit of discussion about how can you interpret the Laplace transform. So I think what you have learned for the lecture notes is simply a definition of Laplace transform. But do you have any idea what actually you have obtained? after doing such integral transform. So you have obtained an expression of some function of s, but what actually does that expression mean? So for example, you have the Laplace transform of omega sine omega t, and you have omega s squared plus omega squared. Then what does it really mean?
Actually, if using sine cosine, I was thinking because it really looks like the 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 funmo really looks like a complex number modulus, and then the funzi really looks like either the real part or the imaginary part.
So are you talking about the numerator and the denominator here?
Yeah.
So did you say the numerator here refer to the real part of something?
Actually, sine and cosine is because if let's say we have a complex number that is s plus I omega, then the denominator will be the imaginary part. Then if it is omega plus I s, then it is the other way around.
Do you mean s equals to omega plus I is?
I mean, if there is an imaginary number that is s plus I omega, then the omega part will be the imaginary part that is now as the sine omega t denominator. However,
So are you suggesting something like this?
yes.
So what does this expression mean?
You mean the denominator or the whole thing?
The whole thing. How do you really interpret it?
It looks very familiar, but I cannot recall.
So any other suggestions? So what epitome is always enchant? How about others?
Oh, I see. I know lah. Imagine a 90-degree triangle. Then the s squared plus omega. So we have the 90-degree adjacent part as s as o and omega, where they are not the same or the same, doesn't matter.
Right
Then
angle.
the hypotenuse will be the s squared plus omega squared. So the s and the omega is actually the representing the sine or cosine of the whole function of the whole triangle.
So sine cosine of the whole triangle.
Yeah, it's like because the two sides of the 90度角 is s and omega, so the hypotenuse is s squared plus omega squared.
You mean as omega?
Yeah, and if we take the lower got now with s and s squared plus omega squared, the hypotenuse and the side s, then if we take that angle, then we will have sine omega t as omega over s squared plus omega squared. If it's cosine, then it's the other.
Okay, but how do you explain this? The Laplace transform of 1 is 1 over s. So how can you use the same analogy to interpret the 1 over S here? So here you don't have sine and cosine, you just have 1.
1. I have not figured out the 1 yet, but I was thinking about the 90-degree triangle. Then I immediately thought of the way that I talked about the imaginary and the real part as a complex plane. If I see the whole Laplace transformed results in a complex plane, maybe it can be something interesting because it is actually a circle if sine and cosine. I mean, but I'm still thinking about the 1.
Right.
1 over S.
Okay, so as I have mentioned at the beginning, actually the S here can be a complex number. So if we write S to be something like alpha plus omega, maybe I omega, then what we have here is something like this, E minus alpha t, E minus I omega t.
Where is the E minus ST?
What?
Shouldn't there be an E minus S? Oh, nothing. Oh, nothing.
So here S
Okay.
is complex, I just simply substitute into.
Yeah.
Right, so whenever you're doing so what you are doing here is actually doing a sort of the product between the function f of t and exponential function. So what you have done here is to use a function. So imagine you have a time series. Maybe it looks something like this. So this is t, this ft. Then you use a function e minus over t and e to the power minus I omega t. So here is an exponential decay, and this is the oscillation part. So what you are doing here is to try to decompose your function f of t in terms of the of this exponential decay and also this oscillation. So so suppose what you have here is the ft to be okay, so I think you should recognize for the Laplace transform of sine omega t and also the cosine omega t here. When you have the s to be equal to minus I omega or plus I omega, then the denominator will be 0, right?
Yes.
So which means when your function ft, so when your basis function y, so when your y to the power minus st, so what you have here is, so suppose you have sine omega t, and then you have y. So now we have s to be equal to, so for example, we have s equals to minus I omega minus I omega t, then this will give you infinity. So it simply means that when your basis functions matches exactly to your ft here, then the integral will diverge to infinity. So suppose you have done the Laplace transform, then you have s. So we have s to be a complex number. But maybe I should not write omega. Beta. And for sine omega t, so this one is omega over s squared plus omega squared. Then you have, so in this complex plane, you have 2 points on the complex plane here, which the Laplace transform diverges. And it simply means your function ft, it contains some oscillation component which has a frequency omega. And you can imagine, so when you do the Laplace transform, okay, let me write it this way. So it will be equal to some expression. So for example, if it is something like this, then here, then for the s which the Laplace transform, for the s which the Laplace transform becomes infinite, they are called the poles. So for the case here, we have s equals to c and s minus d. And for the s which the Laplace transform becomes 0, then they are called the zeros. So in the case here, we have s equals to a and s equals to b. So usually, what is interesting at the poles. So for the poles, they would form some conjugate. So for example, so this one is the Laplace transform with complex s, and then the poles will always happen or will always appear as a conjugate pair, which means if you have something like this, So you have s plus I y, then you always have another pair. I mean another, okay, s minus I y. So what you can learn from the pole here is if the pole, so if the poles appear here, which have some non-zero real component, then it means the ft, the time domain function here, it has some exponential decay component. And for having some imaginary component, so for the pole, it has some imaginary component, it means the function ft here, it has some oscillation component with frequency, so y. So by understanding the behavior of the poles is important is suppose you have some system, some dynamical system that is governed by for example governed by this differential equations. For example, something like this. A very complicated. So actually, have you learned how to solve the PDE with Laplace transform?
ODE, just ODE now for now.
Right. Okay. I think it's still okay. So suppose this is a system. So this is a differential equation that govern the motion of y. But also you can have some external force. So usually you just write as some function t, right? But in more general, it can also be written as a differential equation. So the x here is some external input, and the y here is the output of our system. So if you still remember, then okay, so what is the Laplace transform of a differential operator? So I mean the first thing, so what is the Laplace transform of the first derivative of a function?
Can you repeat the question?
So what is the Laplace transform of the time derivative of a function y?
Oh, it's s times L of y plus f of 0.
Right. So let me write it as y of s. Right, so there are some other terms that depends on the initial condition. So let me simplify. So let me assume all those initial conditions are 0 to simplify the whole thing. Then what you have here is for the nth order time derivative, you have s to the power n times the Laplace transform of y by setting all the initial conditions to be 0. So we don't have those happen. Then after doing the Laplace transform of the differential equation here, then what you have is a n s n plus a n minus 1 s n minus 1 plus something a polynomial multiplied by y is equals to so the way how we solve y is simply by doing some algebraic operations, and y is simply this minus what do I have? Plus one. And minus one s. Right, so this is the Laplace transform of our system input, and this is the output that we want to know. So this looks very complicated, but we can always factorize it as something like this as minus omega as alpha as minus alpha 1 as minus alpha n. Right, so what I want to show here is, even though before you solve, so what you want is y of t, but what I want to show here is, before you really solve the exact solution of yt, you can already observe from the fraction here what would be the property of y of t. So if you still remember what I have mentioned here, so you can really learn a lot about the from the poles here. So if you have s equals to beta 0, beta 1, beta something, then if so, suppose if beta 0 equals to, for example, 2 plus 3i, then you should expect your solution to have some, maybe minus 2 may be more physical. We have a solution that is in terms of e to the power minus 2t, which means you will have some exponential decay component, and also some oscillatory component. It could be 2 sine 3t, sine 3t. So what I'm trying to say here is just to let you have a bit more intuition about what does the Laplace transform really tell you. So the most informative part is really the so-called poles, which tell you how much exponential decay component or the oscillation component have in your solution. So for the zeros, they are less important, and they actually determine how your oscillation component and the decaying component mix together. So if we just want to know the property of a system, then we should look at the poles here. And actually, the Laplace transform is very useful in engineering, and specifically the circuit design or something so-called the control system. But I think you won't learn about them. So I mean, for physics, you only learn about the theory, but you never really learn about how to apply the theories.
Can I ask a question? Because first when we define the definition of Laplace transformation, what we did was to know that because the definition is the integration from 0 to infinity of the function and times the exponent of minus st. So we assume that and then we proceed to thinking that because we want the integral to be finite, so we know that s must be larger than 0. But if we have is it possible that we are having a contradiction now when we put a complex number as s?
So for allowing S to be complex, then what you really required for the solution to exist is really the real part of it. So what you want is f of t to be smaller than t minus, all right, for some big m. So the condition is now for the real part of S.
Okay. So does it mean that the imaginary part doesn't have any constraints?
No. And actually, the Laplace transform is closely related to the Fourier transform. So for Fourier transform is defined as something like this. So you have some normalization factor, but don't bother with it at the moment. So we actually take the form like this, but I think if I take this convention, then probably shouldn't have this factor here. So there is the definition of Fourier transform. So it's basically a slice of Laplace transform by having alpha to be 0. But I think you will learn it in the next lecture notes, I guess.
Okay.
Right, so any questions? Regarding the lecture, your homework that you should submit tomorrow. And let me stop the recording.